For this problem, we're given a object at A that's moving with a rectangular velocity of 100j plus 30k, and we're observing it from B, a fixed location, and we're asked to convert this into spherical coordinates and find the dot values that go with that. Now recall our analysis of spherical systems. We define them from the observer's point of view at O, where you're looking at them with capital R. If you project that down to the xy plane, we have our lowercase r hat direction, and also in this plane would be our theta hat direction, which is a polar ground frame inside of there. You could also relate that in terms of your x and your y values. So we could go so far along the x, up along the y, and vertically up along the z, which would be rectangular. We could come directly along lowercase r and then go up, or we can go directly there in one shot, which would be our spherical coordinate frame. We have VR, V theta, and V phi, the three components of the velocity v, along with, if we need them, the components in the a direction as well, defined by these values here. If we look at our system, the blue vector here would be r. Its projection underneath that would be lowercase r. And then here is the x, the y, and the z value associated with that, which will allow us to write the vector r as -2 in the I hat, plus 2 in the j hat, plus 1 in the k hat, in kilometers, and that's our rectangular system. If we look at the geometry of this system, we get that the magnitude of r is the square root of 2 squared plus 2 squared plus 1 squared, which is the square root of 9, which nicely works out to be 3 kilometers. We should find theta and phi as well, because those three values define the spherical frame. The spherical frame works as r, theta, and phi, where the rectangular frame works as x, y, z. And we've got some information here in the rectangular frame. We need to convert that over to the spherical frame. So theta by definition always comes from x. So it's this angle right here. If we look, this leg is 2, and this leg is 2. That makes that 45. And this would be 90. So theta would be 90 plus 45, 135 degrees. And phi is here. We use it as the angle of elevation. And phi could be found as sine to the -1 of opposite over hypotenuse, where the opposite leg is 1 kilometer and the hypotenuse is 3 kilometers, which will give us a phi of 19.5 degrees. And it's positive, which tells us it's above the plane. If this was below the xy plane, we'd get a negative value from that. So that gives us our geometry. Let's see if we can break up this velocity of A into spherical values. And we'll do it by hand at first, and then I'll show a shortcut on how to do it. So we're given the velocity of A as 0I plus 100J plus 30K in meters per second. And we want to move this to spherical. So first, we're going to need two plane drawings to do this. So draw the X, Y plane. Where this is X, which corresponds to east up here. This is Y. If we look up here, we also have this little R hat direction right here, which makes this angle of 45 with the Y. We're going to need that. So this would be R hat, and that's 45. And technically this is theta. And we know that R hat also has a theta hat that goes with it. It's perpendicular to it. These are at 90 degrees to each other. In fact, they form a polar. So this could also be thought of as an R theta plane. So this is the ground polar plane, where we can see X, Y, and R theta on the same plane. We're also going to need the big R frame, and the big R vector is located in the shaded plane right here, which includes little r, big R, which is right there. It also includes K. Let's draw that plane. So this is going to be the little r, K plane, or big R, phi plane. If we look in at that shaded plane, along the ground we have R hat, and then straight up in the air would be K hat. And from B to A, in that plane we have an angle of phi that we are above little r. Down here, R hat and phi above R hat, and then perpendicular to it is the phi hat direction, and this angle here would also be phi, just like this angle right here would also be 45. Let's look at this velocity. I have 100 on the J, which will show up right here. And K won't show up on this plane, but it would be visible over here. So we have 30 there in the K hat direction. If we had an X component, it would lie down here, and it would not show up on this plane. And what we'll do is break this up into components then. So we need some VR here, and we need a V theta over here, and we use the 45. VR would be 100 cos 45 And v theta will be negative 100 sine of 45. It's negative in the theta hat direction. In fact, that's one of our answers. If we look at the r phi plane, we can cast these two back. And this component right here will be 30 sine phi, where phi is 19.5. And this leg right here will be 30 cos of phi. And they're both positive. We have to come back here and recognize that this VR value here also is visible here. So that VR can also be broken up into components now, where if that's phi, this component here will be VR cos of phi, and this component over here will be VR sine of phi. With that, we can pick up all these pieces and put them together, and we can write the velocity now. V in the r direction will be any of these components over here. So we have 30 sine 19.5 plus VR, which is 100 cos of 45 times the cos of 19.5, right? That's this cos, and VR is over there, which will give us 76.7 meters per second. V theta, we know it's right here, negative 100 sine 45, which is negative 70.7 meters per second. And V phi is this component and that one, which is negative right there. So it'll be 30 cos of phi minus 100 cos of 45, which is VR, times the sine of 19.5, which is 4.69 meters per second. So with that, the velocity of A is 0I plus 100J plus 30K, or it's equivalently 76.7 r hat minus 70.7 theta hat plus 4.69 phi hat, and these are all in meters per second. And it just shows the two different ways that we could write that velocity. We could check it with a magnitude, 104.4 meters per second in both cases. It's always worth doing a check. It's easy to lose one of these signs up here. So two ways of writing the vector. This method takes a fair amount of work, and you have to become very comfortable working in these two planes. And keeping in mind that VR shows up in both. It's down here along the r hat direction. It's over here along this r hat direction. Theta exists only in this plane. Therefore, whatever values we get, we'll be able to keep directly. And phi exists only in this plane. So whatever values we get here, we will be able to keep directly. But the VR is shared between the two. And this is the general format. Take your x and y values, place them on this plane, your xy plane, and work with them, and then export your z value and your VR value from here to solve that one. Now, thankfully, there is an alternative to this method. You may or may not like this alternative. The alternative involves using a transformation matrix. Which allows us to take any rectangular vector, multiply it by this transformation matrix, and it'll feed back the spherical value for us. To use the vector, we need to define theta and phi. So we have theta is 135 degrees, and phi was 19.5 degrees, and as such, to solve for VR, we're going to do row by column, which is how we multiply matrices, where if we're looking for this value right here, we do this row times that column, which gives us 0 plus 66.7 plus 10.02, which is 76.7 meters per second. To get V theta, we need to do this row by column to get that entry, which will be 0 minus 70.7 plus 0 is negative 70.7 meters per second. And then lastly, to get V phi, looking for that, we want to do this row by that column, which will be 0 minus 23.6 plus 28.3 is 4.69 meters per second. And with that, we have our r hat, theta hat, and phi hat components directly. Now, the matrix method is nice for solving these, although it takes some of the understanding of the coordinate frame out of the problem. If you write this as a program in Excel or in MathCAD, it's even easier to do. Now, the second half of this problem involves finding the dot terms. And if we go back to our theorem, we'll see that VR is simply r dot. V theta is r theta dot cosine phi, and V phi is r phi dot. Therefore, this is r dot directly. This is r theta dot cos of phi, and v phi is r phi dot. Recall that r was 3 kilometers, which we need to correct the units here to 3,000 meters. And now we can use this relationship. We get that r dot is 76.7 meters per second. Theta dot we get from here. It'll be negative 70.7 over r cos of phi, which is negative 2.2 10 to the minus 2 radians per second, and phi dot is from this relationship 4.69 over 3,000, which is 1.6 times 10 to the negative 3 radians per second. And that's our spherical dot terms. Now, if we were after the double dot terms, such as r double dot, theta double dot, and phi double dot, they're acceleration terms. And we'd have to be given the acceleration, and then recall, given an acceleration, we would want to break it up into the r, theta, and phi directions, and set those components equal to this value for AR, and notice that the r double dot is the only term that we wouldn't know at this point. The same is true down here. R theta is equal to that, and we can extract that value. And down here, likewise, we can extract that value. Fortunately, that's not that hard to do. We were given an acceleration, let's say 0 I plus 0j minus 9.8 k in meters per second squared, which would put our object in free fall, basically. We would want to get the x, y, and z values converted into r, theta, and phi values. Unfortunately, we could use our same transformation matrix, where instead we would now have the A rectangular terms would go here, which are 0, 0, negative 9.8, and we'll get our AR, A theta, and A phi from that. And again, AR is simply row by column, so it's this row times that column. Now this is very nice. We have a lot of zeros in here. We're only going to keep the last two terms. And this 0, in effect, will wipe out this whole row. That 0 for all the row by columns will wipe out this row. We really end up with this row times that column for each of the terms below. Therefore, AR will be 0.334 times negative 9.8, which is negative 3.27 meters per second squared. A theta will be 0. So we have 0 in the theta hat, and the A phi is that term times that term, the rest of them being zeros, 0.943. And again, we could check this with the magnitude, and indeed it is 9.8 meters per second. And from here, we'd want to set each of these values equal to spherical acceleration. So this will equal negative 3.27. This equals negative 9.24. This equals 0, which does not mean that will be 0. We have to solve for all these terms and extract that. Same up here. We have to solve for this term, knowing the rest. After a fair amount of algebra, you should get that r double dot is negative 1.60 meters per second squared. Theta double dot 1.2, 10 to the negative 3 radians per second squared, and phi double dot as negative 3.36 times 10 to the minus 3 radians per second squared. Although in many cases a theta is enough to solve it. Thanks for watching.